Okay, we are going to look at another rational function and sketch the curve of this function. So again, let's start by looking at the domain. And because it is a rational function, we may have some vertical asymptotes, and that would happen if our denominator was equal to 0. Our denominator is 1 plus x squared, so actually that cannot equal 0. So again, our domain is going to be all real numbers, negative infinity to positive infinity. Okay, let's look for in behavior. So for the rational functions, remember we look at the degree of the numerator, which in our case, the degree of the numerator is 1, and the degree of the denominator, which in this case is 2. And since the degree of the numerator is less than the degree of the denominator, that means we have a horizontal asymptote at y equals 0. Alright, let's find our y-intercept. We do that by plugging in x equals 0, and if I plug in x equals 0, I also get 0. And our x-intercepts, that's going to be anywhere our numerator is equal to 0, and that's only at 0, 0. Okay, so here's the information from the original function. Now it is time for the first derivative test to find intervals where we are increasing, decreasing, any maximums, and any minimums. So to find our derivative, we will need to use the quotient rule. So derivative of the top part is just a 2. Of the denominator is a 2x, and if I plug this into my quotient rule, I get f prime of x equals low d high is going to be 2 times 1 plus x squared minus high d low, 2x times 2x, all over low squared, 1 plus x squared squared. And we can multiply in the 2 and simplify. And if I do that, let's do that down here, f prime of x, I get 2 plus 2x squared minus 4x squared all over 1 plus x squared quantity squared. And simplifying that, I have a negative 2x squared plus 2. So let's factor out that negative 2, and I get x squared minus 1. All over 1 plus x squared quantity squared. Okay, so now I need to find my critical numbers. Critical numbers, anywhere my derivative does not exist, but again, because of the 1 plus x squared in the denominator, it exists everywhere. So anywhere the derivative is equal to 0. So where is that? That'll be at positive and negative 1. So my fence posts for my first derivative test will be at negative 1 and positive 1. And let's test x equals negative 2. And our denominator is actually always going to be positive, so we're really just mindful of the numerator. So if I plug in negative 2, well, x squared minus 1 would give me 3, but I'm multiplying that by negative 2, so I get negative. So this part is decreasing. And then let's try x equals 0, and if I plug that in, I'm going to end up with a negative times a negative, which will be positive, so increasing. And then let's try x equals 2, and again that's going to be negative, so decreasing. So decreasing to increasing to decreasing. Looks like we will have a min at negative 1 and a max at positive 1. So we are increasing between minus 1 and positive 1, decreasing from minus infinity to minus 1, union 1 to infinity, maximum at positive 1, and to figure out the y value of the maximum, we need to plug in the 1 to the original function, and if we do that, we get also positive 1. Minimum at negative 1, and to get the y value for that, we also plug that into the original function, so I get actually also negative 1. So there is the information from my first derivative test, and now I want to find where my function is concave up, concave down, and any inflection points I might have. So I'm going to need to find the second derivative, and that is going to require another quotient rule. Let's rewrite the first derivative. I'm going to actually multiply in that -2, so I get -2x squared plus 2 over 1 plus x squared quantity squared. So derivative of the numerator is a -4x. Derivative of the denominator is a 4x times 1 plus x squared. When I bring down that 2 and multiply by the 2x. And now I am going to plug this into quotient rule. So I will get f double prime. Low d high will be minus 4x times 1 plus x squared quantity squared minus high d low -2x squared plus 2 times 4x times 1 plus x squared, and all over square the denominator. It's now to the power 4. So again, let's be efficient here, and instead of multiplying things out, let's go ahead and cancel out the 1 plus x squared that they all have in common, and then multiply what we have left. So that gets us a -4x minus 4x cubed, and then let's see, that's going to be a -4x times a -2x squared. That's going to be plus 8x cubed, and then a -4x times a 2 is going to be a minus 8x all over 1 plus x squared cubed. Okay, and then we can simplify a little bit here. So we have a 4x cubed, and looks like a minus 12x in our numerator. Let's factor out a 4x. That leaves me with x squared minus 3. Okay, fence posts for my second derivative. Well, the denominator again is defined everywhere, so in the numerator I'm going to have a 0 from the x, and then plus or minus square root of 3. So here's minus root 3, here's positive root 3, and let's see, square root of 3 is about, if we get an approximation of that, 1.7. So for this first interval, let's try -2. And again, my denominator is positive, so really I'm only concerned with my numerator. See, if I do -2 squared, I get 4 minus 3, which is a positive 1, but then the 4x is going to be negative. So this is negative, which means concave down. Here in the next one, let's try -1. So if I plug in -1, I'm going to get a negative times a negative, so positive, which will be concave up. Try plugging in +1, so that's going to be a negative times a positive, so negative, concave down. And then let's plug in +2, and that's going to be positive, concave up. So this one looks like our intervals where we are concave up between -√3 and 0, and then √3 on to infinity. Concave down from -∞ to -√3, and then 0 to √3. And I've actually got 3 inflection points at everywhere my concavity changes from up to down. So I am going to, let's see, I'm going to actually again write them down here. The first one is at the negative square root of 3. So let me plug that into my original function to figure out what my y value is. And it looks like it's about -0.9. And then my next inflection point is at 0. And if I plug that into my original function, that's 0, 0. And then the next one is at +√3. So if I plug that into my original function, I'm going to have about +0.9. Alright, so here is all of my information: increase, decrease, max, min, concavity, inflection points. So now let's graph. Should we adjust our scale any? Everything is pretty normal here. It might be a little bit hard to scale it based on the small numbers, so, well, maybe let's make y, let's make it 0.1 or 1/10 so it's easy to see, and let's keep x +1. And domain is negative infinity to infinity. Asymptote is at y equals 0, so I know that here along my x-axis in the long run my graph will level out. I have at 0, 0 is my y-intercept and my x-intercept, and actually also one of my inflection points. I have a maximum at +1, -1, or +1, +1, so that's going to be here. And then a minimum at -1, -1. I have an inflection point at -√3, which remember is about 1.7. So a little bit before -2, and then -0.9, right there. And then another inflection point at +√3, and then 0.9. So I know that my function starts out decreasing, and it starts out concave down until the inflection point. So maybe something like this. There's my inflection point. Now it's going to turn and become concave up from this -√3 to 0. So it's going to be concave up, hits my minimum, turns, and hits up to my inflection point, and then it's going to be concave down up until my next inflection point, and I know it's increasing on this interval, and then it turns and it's going to become concave up, and I know it's got to level out there. So my graph looks something like this: concave down and decreasing, concave up, then concave down again, and then concave up here.